Okay, so I believe all of you have learned vectors before in your secondary school. And whether it's SPM or IG, I believe you have all learned vectors before. If any of you has never learned vectors before, please let me know now in chat. If you have never learned vectors before in SPM or IG, please let me know in chat now. Okay, so I assume everyone has foundation knowledge in vectors. Uh, the major difference between SPM or IG vectors with A-level vectors is that now we focus on three-dimensional vectors. Okay. In 99.99% of the past year questions involving vectors in our A-level syllabus, it will be three-dimensional. It will be three-dimensional. Okay. So the first point, a vector has both magnitude and direction. Geometrically, a vector can be represented by a straight line with an arrow. And so usually when we want to visualize a vector, we will draw a straight line with an arrow like this. Some people draw the arrow at the end, that doesn't matter. Right, so point number two, if this is a line from P to Q, if this line segment is from P to Q, then the length of the line PQ will represent the magnitude of the vector. And so in this chapter, when we mention the word magnitude of a vector, it means the length of that line segment representing the vector. And magnitude and length, I'm going to use it interchangeably in this chapter. And so when I say length, I mean magnitude. When I say magnitude, I mean length. Okay. Hey, well, the arrow on the line PQ, of course, represents the direction of the vector. Okay. Point number three, notation. A vector can be written as PQ with an arrow above it. And so if it is a vector connecting point P to point Q, we can call it PQ with an arrow above it. And it is important for us to write the arrow on top. Because if we do not write the arrow on top, if you just write PQ like this, it will be understood as the distance between P and Q. Distance between P and Q, which is also the same as the length of line segment PQ. And so if what you intend to mean is the vector, then it is compulsory to write the arrow above it. And so make sure you use correct notation. Okay. Vectors can also be written in small letters in bold, like A printed in bold here. And so if it is in printed form, sometimes they may introduce small letters. A printed in bold. So this letter is in bold. And so whenever you see a bold small letter, it means vectors in printed form. So some examples here, like this I and J printed in bold, these are all vectors. I, J, K are all vectors. Small letters printed in bold are all vectors. It is for a printed form, right? However, when we write by hand, it's hard for us to write something in bold, right? So when we write by hand, we use an alternative notation. And so in printed form, they are going to print this letter A in bold. But in handwritten form, we are going to write the letter A with a curly line or a squiggle below it. So this curly line here is also compulsory. And so when you write a vector in small letter, in handwritten form, it is compulsory to draw the curly line below that letter. Okay. I repeat, it is compulsory to draw the curly line below that letter when you write a vector in small letters in handwritten form. Because it's hard for us to write things in bold. And so I only accept A with a curly line below it when you handwrite. Okay. Right, point number four, a vector can be expressed in two forms. We have magnitude direction form and component form. Magnitude direction form is actually won't be asked in the exam. This one won't be asked. Okay, so magnitude direction form, we actually can ignore it because it won't be asked in the exam. Just in case you are wondering what is magnitude direction form, it's only applicable for 2D vectors. Yeah. Okay. And this one is only applicable for two-dimensional vectors. Okay. And just in case you're curious, I'll just give one example here. Okay. Let's say I have a two-dimensional vector that makes an angle of 30 degrees with respect to the right-hand side direction. And with respect to this horizontal, it makes a 30 degrees. And let's say it has a length of 5. And let's call this vector A. So in magnitude direction form, we can write A is equals to bracket 5 comma 30 degrees. And this is in magnitude direction form. Yeah. So it will be written in bracket consisting of two numbers separated by comma, where the first number represents the length and this number represents the angle measured from the positive x direction. And so another example, if you have, let's say, this angle here is, let's say, 225. It measured from the positive x direction. Positive x direction means the right-hand side direction. And let's say this has a length of 3. And this is a vector b, then we can write b is equals to 3 comma 225 degrees. Yeah, in magnitude direction form. Okay. However, magnitude direction form is only applicable for two-dimensional vectors. That's why I say it won't be asked in the exam, because 99.99% of the exam question will be 3D vectors. Okay, so our focus here is only the component form. Here's our focus. We only focus on this form. Yeah, so magnitude direction form, you can actually ignore it. We only learn component form actually, right? So in component form, for 2D vectors, I think everyone has seen it before. It can be written as a number times I plus a number times j, where I and j are known as standard unit vectors. Right? So the vector I means it is a vector of length 1 unit. In the positive x direction, and j is vector of length 1 unit in the positive y direction. I believe we have all seen this before, the I and j. And so it will still bring the same meaning, just like what you learned in SPM or IG. Okay, so there's a more compact way of writing it. So instead of writing xi plus yj, most of the time when doing computation, we prefer to write it in a vertical bracket form, where we just write the coefficient of I and j. Okay, so one quick example here. Okay, this is a two-dimensional diagram. Okay, so in a two-dimensional diagram, there is of course x and y axis, and we also call this a Cartesian plane. Okay, so suppose that I have a vector connecting point A to point B. Let's say making 2 units to the right, 3 units up. Okay. So the vector AB, we can write it as 2i plus 3j. Okay. Notice that in handwritten form, the I and j has a curly line underneath it. It is compulsory to write curly line because I and j are vectors, they are not normal numbers. In vertical bracket form, we can also write as 2, 3. Okay. As simple as that. Okay. Then, of course, if you have it pointed to some other directions, then it can have negative coefficients. So for example, if this is point C, so it will move, let's say, minus 2 units to the left and minus 1.5 units downwards. then vector from A to C, it will be -2, -1.5. To the left means minus, negative coefficient for I if it's to the left, negative coefficient for J if it's going downwards. Right, so it will be -2I minus 1.5J. Okay, done. Right, in 3 dimensions. Okay, now in our syllabus, one good news is they won't require you to draw 3-dimensional diagrams. I repeat, they will not ask you to draw 3-dimensional diagrams. However, if you are able to visualize a 3D diagram, it will help you in your understanding. If you find it hard to draw 3D diagrams, don't worry, you will not be asked to draw 3D diagrams because 3D diagrams are just hard to draw. But it will be helpful if you can visualize a 3D diagram because that will help you in your understanding. Okay. Wei Feng asked in chat, is it preferable to use decimals or fraction? We always prefer fraction. We always prefer fraction. Yeah, so the 1.5 here actually, the preferred form is -3/2. Yeah, we actually prefer fractions. We prefer fractions. It's just like other chapters. We prefer fractions more than decimals. Okay, now, first of all, to introduce to you how I usually would visualize a 3D diagram, or just to set up the mindset first. Okay, now in 3D, okay, if this is the first time you see a 3D diagram, this is to help you visualize how a 3D diagram will look like. Okay, so you can imagine like there is a table. Okay, there's a table. Right, then you have your x-axis that is on the surface of the table. Just imagine you put a pencil on the table surface, right? And the direction of your pencil represents the x-axis. Okay. Then you also have another pencil on the table, and you put it in this direction, and so that will be the y-axis. And so both x and y-axis, they are on the table surface. They're on the table surface, and you have a 90 degrees here. Then now you also imagine that you have another pencil that you hold it vertically. You hold it vertically. You hold it vertically such that it is perpendicular to the table surface. Right. Then this vertical pencil here, and you take it as the direction of the z-axis. And so this is how we would visualize a 3D diagram. And so you imagine there is a horizontal surface. Yeah, it doesn't necessarily need to be a table, but this is just helpful for us to understand it. And so you imagine there's a table surface, a horizontal surface. You have an x and y axis. You have x and y axis both lying on the table surface, and you have a z axis which is in the direction perpendicular to the table surface. Right. So that means that whenever we draw, okay, maybe I redraw my z axis. It's like this. And so there is a 90 degrees here formed between y and z axis. There's also another 90 degrees here formed between x and z axis. And so x and y directions are perpendicular to each other. Y and z are perpendicular. Z and x are also perpendicular. And so x, y, z axis, they are pairwise perpendicular to each other. Okay. Okay. So if you can see the diagram that I print out there, this one. And so this is how we usually draw a 3D diagram. But you won't be asked to draw. This is how we usually draw a 3D diagram. And so we'll just draw the x, y, z axis like this. Right. And then they will of course share a common origin, a common 0 for all the 3 axes. Right. And so in this diagram here, okay, they measure 3 units to the left. Right, and then they also measure 2 units in the positive y direction, and they measure 4 units vertically up. Yeah, so in this diagram, this point here, okay, so in a normal xy plane, in a 2D plane, and when you have a coordinate, let's say this is 3, this is 4, and the coordinates will be written as 3, 4. Okay. So similarly, when you have a 3D diagram, when you have 3D diagram, the coordinate will have 3 numbers, okay, all separated by commas. Okay, and as usual, the first number represents x coordinate, second number is y, third number is z coordinate. Okay, referring to this diagram on the right, the vector from the origin O to the point A. Okay, so let's name this as point A. It can be written as OA equals to minus 3i plus 2j plus 4k. Okay, so k is a standard unit vector in the z direction. Ij still mean the usual meaning. Ij still bring the usual meaning, where I is 1 unit in the positive x direction, j is 1 unit in positive y direction, k will be 1 unit in positive z direction. Okay, so we move minus 3 in the x direction, 2 in the y direction, 4 in the z direction. Or if you prefer vertical bracket form, it is minus 3, 2, 4. Okay, like this. Okay, done. Next. Right, next is on the concept of unit vector and position vector. This might be something that you have learned before briefly in your SPM or IG syllabus. Now we are focusing much more on position vector. Position vector is particularly important in our syllabus. In your SPM or IG, you might have learned about it briefly. Here we focus a lot on position vector. Okay. So first of all, what does a unit vector mean? A unit vector, by the word unit, it means the length is 1. Length is 1 unit. Right? So a unit vector means a vector with length of 1. Okay. So unit vector in the direction of a vector r, denoted as r hat. Yeah. So if you have a vector a, then a hat means unit vector in the direction of a. Okay. Right. Then it is defined as r hat equals to r divided by length of r. Right, so you can imagine this. If my vector r, let's say it has length of 5 units, then if I want a unit vector in the same direction as r, then I just need to shrink the length. Right? So I just need to get a vector, a much shorter one, 1/5 the length of r. 1/5 the length of r. This will be the unit vector in the direction of r. Okay, so 1/5r, if you notice, this is actually equals to r divided by its own length. Yeah, I think you all know that modulus of a vector means the length. Okay, so this is actually the length of r, the notation for length of r. And so whatever vector divided by its own length will give you the unit vector. And so that's why we have this formula. A unit vector in the direction of r, there is a notation for it. So if you write r with a hat up there, it means the unit vector in the direction of r is equal to r divided by its own length. And some people prefer to write is 1 over length of r times r. It means the same thing. Okay. Okay. And how to find length in 3D? We are about to cover it. It's just the next page. Okay. Anyway, let's continue here first. Right, the position vector of a point P is the vector from the origin O to the point P. So this introduces you to the concept of position vector. Okay, so for whatever point, whether it's in a 2D space or in a 3D space, the meaning of position vector is the same. It's always a vector directed from origin O to the point P. So for example, let's say this is a 2D diagram, 2D diagram with a usual x and y axis. If I have a point P with coordinates 3, 4, and then if the question wants you to find a position vector of P, what it really means is it wants the vector from O to P. And to get the vector from O to P is very easy. You just need to look at the coordinates of P and convert it into vector form. Because to get from O to P, you will of course need 3 units to the right, then followed by 4 units up. So it will be 3i plus 4j, or in vertical bracket form, just 3, 4. So to get the position vector of a point is easy. If you know the coordinate, you just need to take the coordinates, take the numbers in the coordinates, and distribute it as the coefficients I and j respectively in the same order. And then you will get position vector. So if you are given a point with a known coordinates, and they ask you to state the position vector, there's no computation involved. Just look at the coordinates and convert it into vector form. You should away get position vector. Okay, next, in a 3D diagram. Okay, so let's say I have a x, y, z axis. And let's say I have this point here with, let's call it point A. This with coordinates, let's say 2, 5, 6, something like this. Right, this is some floating point in a 3D space. Right, so if you're asked to find position vector of A, just look at the coordinates and distribute to the ijk. So it's 2i, 5j, 6k. Or in vertical bracket form, 2, 5, 6, just like that. Okay. So similarly, if you are given the position vector, okay, this is actually equals to OA. Yeah, so similarly, if you are given, let's say, OB is equals to the vector minus 4, 3, 5, then you can straight away tell coordinates of B will be minus 4, 3, 5, just like this. Just copy back the same number, but in a different form. So when we talk about coordinates, it must be presented in coordinate form, and numbers separated by commas and listed horizontally. This will be coordinates. If they want position vector, then you either list out the number in vertical bracket, or you can also say minus 4i plus 3j plus 5k. Yeah. Okay. This is actually very simple things. You just need to use the correct form. I said if it is a vector, a position vector, it must be in vector form. If it's coordinate, it must be in coordinate form. Just make sure to use the correct form. The conversion between these two is actually very easy. Okay, next. Okay, on standard unit vectors. Okay, so in 2 dimensions, which you all are familiar with, the standard unit vectors are I and j. I means a movement of 1 unit in the positive x direction. J will be movement of 1 unit in the positive y direction. So if we only talk about 2D vectors, then when you write in vertical bracket form, because I can always be written as 1i plus 0j, then of course you can convert to 1, 0 for the case of a 2D vector. And similarly, j can be written as 0, 1. Okay. So in the Cartesian coordinates, meaning that in a normal 2D diagram with your xy axis, right? So for any point, let's say P with coordinates 2, 3, then you can always write OP equals to 2i plus 3j. Yeah. Okay. In our syllabus, our focus is of course on 3D. So the standard unit vectors are I equals to, okay, so here in 3D, in 3D, our vertical bracket form of vector must have 3 numbers. Must have 3 numbers. And so because I can always be written as 1i plus 0j plus 0k. So when you convert it to vertical bracket form, it will be 1, 0, 0. Yeah. And similarly, j is 0, 1, 0, and k is 0, 0, 1. K will be a movement of 1 unit in the positive z direction. Okay. Yeah. Okay. Let's move on to the next page on how to find length of vector. Okay. Length of vector in 2D, everyone knows. For the case of a 2D vector, okay, if I have a 2D vector, let's say this vector A is the vector 2, 3, like this. Right, then to get the length of A, length of vector A is just square root of 2 squared plus 3 squared. It's just an application of Pythagoras theorem. Okay. So one good news is for 3D, for 3D, Pythagoras theorem will still apply here, but it's just an extension of Pythagoras theorem. Okay. You just take x, y, z coordinate, the x, y, z components, or the coefficients of I, j, and k, just square them separately, add all of them up, and you take the square root. And that will give you the length in 3 dimensions. This is actually just an extension of Pythagoras. And so Pythagoras can be extended to 3D. Okay, I will not go through the derivation here. If you're interested, you can try to search for it online or try to derive on your own. We'll just focus on how to apply the length formula. It's basically just a Pythagoras theorem applied multiple times. Then it's possible to get this formula in a 3D diagram. Okay, so if you have a vector, I think I have an additional equal sign here. Okay. Oh, I think I have a missing vector A here. Yeah. Yeah. So if the vector A is the vector PQ and it has xy, then the length of A or the length of vector PQ will be given as this formula. Yeah, I have a missing vector A then. Okay. So one example. Okay, if my vector AB is 2i minus 3j plus 4k, then the length of AB, the modulus of a vector means the length of that vector. It will be 2 squared plus minus 3 squared plus 4 squared. And then you will get some numbers, units. If you forget to write the word units, don't worry, because you will not be penalized if you forget the units. Okay. And if you're wondering whether it is compulsory to write this negative here, this negative is okay to omit. And because when you square a number, that negative will disappear anyway. Okay. Okay. Example 1 is a very simple practice just to warm you up. The first two questions are on 2D. It's just for you to recap on your SPM or IG knowledge. Then part C and D is just the same technique applied to 3D. Okay, so for part A, state the position vector of the point A and B. The position vector of A is actually the vector OA. And just by looking at the coordinates, you can tell it is 3i plus 4j. Or equivalently, you can write 3, 4. Either one will do. You only need either one form. Right, also, when you present your working, if you just write OA, equal to 3i plus 4j, it's actually good enough. Because a vector directed from O to A will be understood as the position vector of A, even if you don't mention the word position vector. Whenever we see OA, it will be understood. Understood as position vector of A. It's understood. And so if you don't want to mention the word position vector, it's fine. As long as you write vector OA, it will be understood. Still in part A, position vector of B. That will be OB. That will be minus 5I plus 6J, or in vertical bracket form, minus 5, 6, and that's it. Okay. Now, before I move on further, on the concept of position vector, let me show you some past year questions first, at the back of the chapter. Right. Now, in many of the past year questions, it will be phrased like this: relative to an origin O. Okay, the position vectors of points A and B are given by so and so. Okay, so usually in the past year question, in many of the past year questions, they are going to tell you relative to an origin O, which means that the position vector are all starting from O lah. So O is the starting point lah. So by saying relative to an origin O is trying to tell you that all these position vector, they have a starting point at O. Okay. Right. Sometimes, but very rare, it's very, very rare. So if they say relative to the point A, relative to the point, okay, let's call it N, relative to the point N, where the position vectors of A and B are something. Okay. So if they say relative to the point N, right, that means N will be the starting point. So they are actually talking about vector NA and vector NB. When they say position vectors of A and B relative to N, then what they mean is NA and NB. But this is very rare. In 99.9% of the exam question, it will be relative to the origin O. Okay. And if the question doesn't say, okay, so if this phrase here in yellow is not present, if I delete away the phrase here, when you see position vector, we are going to assume, we will assume that the starting point is O. But there are some exam questions that didn't tell you relative to an origin O. Right? So if you see the word position vector and they don't tell you where is the starting point, then by default we will assume that the starting point is O. Right? So that is a usual practice. Let me see whether I can find a question that doesn't tell you relative to origin O. It's very rare. Usually they will tell. Yeah. Yeah, you can see in most of the question they will say relative to an origin O and so on. Okay, so yeah, on the rare occasion that they don't mention relative to O, you will assume that the starting point is O. Okay. Yeah, it's very rare for, yeah, I almost never seen before relative to a point other than O. This one is very, very rare. This one is very rare. Okay. Now, let's come back to the example 1 just now. Let's continue with part B here. Find the unit vector in the direction of r equals to 2I minus 3j. Okay. Unit vector in the direction of r. Okay, the notation is r hat. So if you mention r hat, then it's okay not to mention the phrase here. This phrase I underline in green, it's okay not to mention it if you mention r hat, because they bring the same meaning. So r hat, the formula is the vector r divided by its own length. Okay. So what is your vector r? Your vector r is 2I minus 3j. the length of R will be 2 squared plus negative 3 squared. And then the bottom will give you square root of 13. 2I minus 3j. And so it is usual practice for us to write your I and j terms separately. So we would usually prefer to write 2 over sub 13I minus 3 over sub 13j. And we'll take this as a final answer. The coefficients of I and j written separately. Okay, to those who prefer the vertical bracket form, of course you can. You can convert it to vertical bracket form. That will be 2 over sub 13 minus 3 over sub 13, and that's it. Okay, now let's continue with part C. Let's take the position vector of C and D, and this one is simple. Position vector of C will be the vector OC, which is 2 minus 1, 3. If you prefer, you can of course write in terms of ijk, that's 2I minus j plus 3k. Still in part C, position vector of D, that will be OD, is minus 3, 0, 5. In terms of ijk, it will be minus 3I. The 0j is okay not to write. You can just write plus 5k. Yeah, both forms are acceptable. You only need either one. You only need either one. Yeah, in the exam, you don't have to give both forms. One thing to be careful about when you want to convert from the ijk form into the vertical bracket form is that if this ijk form, it has a missing j term, remember to fill in a 0 there. For the case of a 3D vectors, it must consist of 3 numbers. It must consist of 3 numbers. And so if the j term is not present in the ijk form, you have to fill up a 0 on your own. You cannot leave it blank. In the vertical bracket form, you cannot leave the number blank. So if it is a 0 coefficient, it is a must to fill a 0 there. Okay. Then for part D, unit vector in the direction of 2I minus 3j plus 4k. Okay, so your R here is given as 2 minus 3, 4. Okay. At this time, I choose to do it separately, like I find the length first. It's actually your choice whether you want to find R hat straight away or you want to find the length separately first. It's your preference. So this time I choose to find the length first. That's 2 squared plus negative 3 squared plus 4 squared. So using a calculator, you have 4 plus 9 plus 16, set of 29, unit. R hat, it will be R divided by its own length. That will be 1 over set 29 times 2 minus 3, 4. Well, there's nothing wrong writing 2 minus 3, 4 over set 29. This is actually correct. There's nothing wrong writing this. But we usually, like when you have a vertical bracket form divided by a number, people usually prefer to write this number here as a fractional coefficient because it looks nicer that way. Yeah, so okay, so whether or not you distribute your division of set 29 into the bracket, is actually optional here. Okay. These two forms, they are actually regarded as equally simplified. Both are equally good to be left as final answer because even after you distribute your deviation by SET29 into the bracket, nothing gets simplified actually. Nothing gets simplified. So yeah, so sometimes you might see the answer being given in this form, where they factor out the fractional coefficient. And because these two forms are regarded as equally simplified. Of course, if you want to write in terms of ijk, it will be this like 2 over SET29I minus 3 over SET29J and plus 4 over SET29K. Okay. Right. So talking about simplified forms, if you are given a vector like this, let's say your final answer is 1 over 2, 6, 8, 4. Okay. So this one, you are expected to multiply your half inside because after you multiply your half, all three numbers get simplified. 3, 4, 2. Okay. This one you are expected to multiply your half inside because this is considered more simplified. Right, so they would expect you to multiply your half inside, so and hence preferred. Right, so if you leave your half at the outside, you might lose the final answer mark if it is numbers like this, where all of them can get simplified. Okay. So, however, if your answer is like something like half, 6, 8, 5, then it's actually okay to leave it this way. It's actually okay to leave it this way because not all three numbers can become simplified after you distribute the half. It, particularly this number 5 here. When you distribute the half inside, it's just 5 over 2. It doesn't get simplified. Although 6 and 8 can be simplified, but 5 cannot get simplified. So in such circumstances, 6, 8, 5, and 3, 4, 5 over 2, these two are considered to be equally good. Equally good as final answers. And so I hope everyone is clear with this. And so if all three numbers can become simplified after you distribute in the coefficient, then you are expected to distribute in. And however, if not all three numbers can become simplified, then it's your choice whether you want to leave the half at the outside or you want to bring the half to the inside. Okay. Most of the time, when we do computations in the later parts of the chapter, we will usually just distribute all the coefficients inside. Most of the time we'll do that. And because after you distribute the coefficients inside, right, it's easier to read. It's easier to read the information. Okay. Okay, the time is now 9:31. That's the end of the first hour. So let's take a short break. Yes. Then we will move on to page 3. You come back in 7 minutes. Right. Hi everyone and welcome back. Now let's move on to the third page on equal vectors. So under what situation or under what condition do we say that two vectors are equal? Okay, two vectors A and B are said to be equal if the vectors A and B have the same magnitude and direction. So there are two conditions to fulfill: same length and same direction, and same length and same direction. And then only we say the vectors are equal. So the diagram here shows you four vectors which all have the same direction and they all have the same length. You need same direction and same length for you to claim that vectors are equal. So all four of these vectors A, B, C, D, they have the same length and same direction, therefore they are all equal vectors. And so we can write vector A equal vector B equal vector C equal vector D. Okay, so the reason why I give you this diagram here, four equal vectors, is to tell you the concept of free vectors. So vectors are free, all vectors are free in the sense that uh, they do not have a fixed position and can be moved around freely, which means that if you move a vector uh, to a different position, as long as the length and direction remains the same, you can still call it using the same name. Okay, so what I mean is this. Okay, I will just illustrate using a simple 2D diagram. Uh, okay, so if I have a vector uh, pointed from point A to point B, okay, and let's say this is 3 units, this is 1 unit. Okay, now we can of course call this vector AB. We can call this uh, vector AB. Now, if I move this, if I move this vector and I place it here, if I move the vector and I place it here, maintaining the length and direction, so that now it starts from O, but I still maintain. Let's say this is the ending point is now P. It still maintains the same direction and same length, so it's still 3 units to the right and 1 unit upwards. Okay. Now, after I move it, although now the vector is connecting point O to P, we can still call it this vector as vector AB. There's nothing wrong to call it a vector AB, although it connects point O to point P, which are two different points, but you can still call this vector as AB. In fact, we can say the vector from O to P is the same as the vector from A to B. They are equal vectors because OP and AB, they have same direction and same length. Okay, so yeah, this is a very important kind of mindset in the chapter of vectors. So be aware that vectors can be moved. Vectors can be moved to a different position and still retain the same name. It can be done. And after you do that, after you move the vector to a different position, you can still call it the same name as long as direction and length remains the same. Okay, so when you move a vector around, make sure that the length and direction remains the same. And then only it can retain its original name. Okay. And so as we go further into this chapter, this kind of mindset will be important, and the concept of free vectors. Okay. Then next is zero vector. Okay, a vector of zero magnitude can be in any direction. It's denoted by zero in bold if it is in a printed form. If it's a written form, we will write zero vector equals to 0 with a curly line underneath it. So for the case of 3D, it will be equal to 0i plus 0j plus 0k, and which is just 0, 0, 0. Okay, so what do you mean by a zero vector? You can imagine a zero vector as just a dot. It it's only a dot. So in the 3D diagram, yeah, if this is a zero vector, then it's only a dot. So if it's a zero vector, then it's only a dot. Or basically, it's nothing. So if it is only a dot, right, it has no length. Because yeah, and if you really apply the formula, right, the length will be 0 squared plus 0 squared plus 0 squared. It will be 0. It has 0 length. Because you don't even have an arrow to measure the length. Okay. And because it's just a dot, you can't draw it using an arrow. So since it's only a dot, it has no direction, or some people can interpret it as it can take any direction. And so it's not wrong to say it has no direction. It's also not wrong to say it can take any direction. Because it's only a dot. So it doesn't have a fixed direction. Okay, next, on negative vector. Okay, in 2D, you have learned before negative vector in your secondary school. In 3D, the same idea applies. And so the negative of a vector A written as negative of A, it is defined by a vector with the same magnitude as A but in the opposite direction. Which means if your A looks like this, then the negative of A will have the same length but in the opposite direction. And this is applicable to both 2D and 3D. In fact, whatever that we have learned so far, they are applicable to both 2D and 3D. Yeah, so taking the negative of a vector simply means we are reversing the direction, but we retain the length. Reverse direction, but retain the length. Opposite direction, but same magnitude or same length. Okay. Next. Scalar multiplication, not to be confused with scalar product. Okay, well, scalar product, I believe this is something that many people have never heard before. Okay. Scalar product is something that we will learn in section 9.2 of this chapter, which is on page 10, I think, yeah. Scalar product is a totally different thing, and not to be confused with scalar multiplication. Okay. Scalar product, we'll talk about it later when we cover section 9.2. For now, we only talk about scalar multiplication. Okay. So when we use the term scalar multiplication, okay, what we mean here is we multiply a vector with a number. We multiply a vector with a number. Okay. And in the chapter of vector, we tend to use the word scalar to refer to a usual number. Scalar is just a more fancy name for number. And when we talk about the chapter of vectors, when you see the word scalar, it's just a more fancy name for number. Right, so this number 2 here, in front of the A, this will be known as a scalar. It's just a usual number. Right, so when you multiply a vector with a scalar, the effect of the scalar is that it modifies the length. It either lengthens it or shortens it, depending on whether that number is more than 1 or less than 1. So if this number here, the scalar here is more than 1, then it lengthens it. The vector becomes longer. So when A becomes 2A, when you multiply by the 2, then the length is doubled. This one has a length doubled. Then if you have a fractional coefficient, for example, if this is my vector B and this is half B, then it actually shortens it. So this length is half. Length is half. Okay. Yeah. And one thing to notice is that when you multiply by a positive scalar, whether it's a number more than one or less than one, as long as the scalar is positive, if scalar is positive, that means the direction maintains, direction remains the same. If the scalar is negative, then the direction is reversed. And so the second diagram in the box, the second diagram in the box here shows that when we multiply by a negative scalar, right, so the negative sign itself, it reverses the direction, right, while the number of 3 over 2, uh, it lengthens it, it lengthens it, it lengthens the vector by a factor of 3 over 2. Which means the length of EF, the length of the vector EF is actually 3 over 2 times the length of vector AB. It lengthens the vector by a factor of 3 over 2. And so for example, if your AB is 1 cm, then your EF will be 1.5 cm. It lengthens it by a factor of 3 over 2. Right. The negative will reverse the direction, right, while the absolute value of that scalar, it will have effect on the length. Okay. Yeah, so the sentence under the box says if the constant or if the scalar is negative, then it reverses the direction. I've covered it just now. Next is on parallel vectors. Okay, parallel vectors is very important in our syllabus. We'll keep using this concept again and again for the next 3 weeks or so. Okay, so be very clear with the concept of parallel vectors. Okay, so when we talk about parallel vectors, we will always involve non-zero vectors, because it is meaningless to talk about direction when you have zero vectors. Okay, so if you have non-zero vectors A and B, and if you are given that these two vectors are parallel, then it is always possible to write vector A as a scalar multiple of vector B. Okay, so you have been introduced to the concept of scalar multiplication. So when we say vector A is a scalar multiple of vector B, it means A is equals to K times B, where K is a scalar. And sometimes some books may also phrase it as A is equals to K times B for some scalar K. Okay, okay. So notice that here we didn't mention that K must be positive or negative. In fact, even if K is negative, the two vectors are still parallel. So the condition that you should memorize is this. Is this sentence here. Okay. The double slanted line we have seen before. Double slanted line means parallel. And so we say A is parallel to B if and only if A is equal to KB for some scalar K. Okay, so there are actually, okay, I can draw some diagrams here for you to visualize. Okay, if my A goes this way, then my B is just a shorter version. Okay, then of course A and B are parallel. And so in this case, they are parallel. In this case, we say A is parallel to B. Okay, now if I give you another example, if my A goes this way, okay, maybe I use a different symbol. If my C goes this way, and my D goes the opposite direction, okay, we still say C is parallel to D. We still say C is parallel to D. And so, in terms of directions, there are two possibilities, which means that if we say two vectors are parallel, okay, two vectors are parallel, then we can deduce that the two vectors either have the same direction or opposite direction. And so parallel vectors doesn't mean same direction. There are two possibilities. If you are only told that vectors are parallel, then they can have same direction or opposite direction. There are two possibilities. I repeat, parallel doesn't necessarily mean same direction. Parallel can mean same direction or opposite direction. And you will need more information in order to verify whether they are the same direction or opposite direction. Be aware that there are two possibilities regarding direction of parallel vectors. Either same or opposite. Okay. Now, okay, so if I give you a numerical example here, let's say in my first diagram in the red color, my vector A has length 3 units. And my vector B has length 1 unit. And then if you want to write A in terms of B, you can write A equals to 3 times of B. Right? Everyone agrees, right? A equals to 3 times of B. But if I rearrange my equation and I write B is equals to 1/3 of A, it's also correct, right? Both of these equations are correct based on my diagram. Right, so this means and in fact, from this equation itself, you can always rearrange it and write B is equal to 1 over K times A. Right? Then if I rename my 1 over K as a different symbol, let's say I write B equal to lambda A, where lambda is just 1 over K, then it is also true for me to say, B is equal to lambda A for some scalar lambda. Right, so this statement and this statement, and the two statements that I color in light blue color, and the two statements in light blue color, they actually mean the same thing. They actually mean the same thing because you can always obtain one statement from the other just by moving the scalar to the other side and then rename it. Right, so so just be aware that when you have the information of parallel vectors and you need to form your own equation, I mean, convert parallel into equation. Convert information on parallel into equation. It is actually your choice whether you want to write A equals KB or B equals KA. It is your choice. It is your choice because both versions are correct. Right? But of course, if you write B equals KA, right, and if you eventually solve for K, this K will be a different value. Okay. Right, so if you are given A parallel to B and you want to convert it into equation, it's either A equals KB or B equals KA. It's your choice. Yeah, because both are correct. Okay. Then okay, part A says that if the scalar K is greater than 0, which means if K is positive, if K is positive, that means A and B are in the same direction, just like my diagram in red color. And so if the scalar here, whether it's 3 or 1/3, they are both positive. They are both positive. Right, so A and B are in the same direction as you can see in the diagram. Right, so if K is negative, just like my second diagram, if I have two vectors in opposite directions, then the scalar that you get must be negative. Right, so if I try to write C equals to K times D for some scalar K, then this K here must be negative. It must be negative. And then only it's possible for them to have opposite directions. Okay. Point C tells you that if K is exactly equal to 1, then A and B will be the same vectors. A and B will be equal vectors. And this one should be obvious. In the equation, if we set K to be equal to 1, then of course A is equal to B. And when vectors are equal, they have the same direction and same length. Okay. Part D says if K is equal to -1, then A and B will have the same length but opposite direction. And this one should be also obvious. Okay, next. On collinear points. So in the chapter of coordinate geometry, you have learned before the concept of collinear. So here is the same concept, but we are just studying it using the vector mindset. Okay, so if they say points A, B, C are collinear, that means it is possible to connect A, B, C using a same straight line. A, B, C lie on the same straight line, then we call them collinear. The points are collinear. Okay, so if we have a diagram like this where A, B, and C lie on the same straight line, then okay, you can even put your C very far away. It doesn't matter. As long as they lie on the same straight line, we say they are collinear. Well, then if you try to form vectors, using points A, B, or C, using either two of the 3 points, you try to form vectors. So you can form this as vector AB. You can form this as vector BC. You can also form this as vector AC. Okay, or I can also form this BA, CB, CA. Right, so there are so many vectors that we can form using two of the 3 points. Right, so regardless of what vectors you form, as long as you take 2 out of the 3 collinear points, all the vectors that you form will be parallel. And so all the purple color and the red color vector that I draw there, they are all parallel to one another. So all the 6 vectors that I draw on my diagram, they are all parallel to each other. Which means if you simply take a pair of vectors to compare, let's say if I compare AB with, let's say AC, I can confidently say that they are parallel. If I take a different pair, let's say BA, I compare with AC, I can also confidently say that they are parallel, as you can see in the diagram. Remember, parallel doesn't necessarily mean same direction. Opposite direction is also parallel. Opposite direction is also parallel. And that's why it is perfectly correct to say BA and AC are parallel, although they are pointing in opposite direction. Where is my BA? BA is here, right? And AC is here. Although they are pointing in different directions, it is okay to say that they are parallel. Because opposite direction is also parallel. Okay. Well, if you need to prove that 3 points are collinear, so these are the conditions to establish. You need to establish these two. Establish these 2 points, these 2 facts, to prove that A, B, C are collinear. Okay, so the first thing to prove is that you need to show that 2 vectors, each connecting a pair of points among A, B, and C, are parallel. So what I mean here is you need to take, for example, A, B, and AC, show that they are parallel. Then notice that there is a common point involved, which means if you take A, B, and AC, A is a common point. And then if you take BA and AC, A is a common point. So there must be a common point. And then only you can claim that they are collinear. So there are 2 things to establish. Okay, next. Okay, properties of non-parallel and non-zero vectors. So if you have 2 non-parallel and non-zero vectors A and B, if HA equals to KB, then H equals to K equals to 0. So what it means is this, H and K are scalars here, and here HK are scalars. Okay, so what they mean here is this, non-parallel and non-zero vectors. Okay, so let's visualize the diagram here. Okay, non-parallel means that they must be pointing in different directions. And they can't have the same direction, they also can't have opposite direction. So for example, my vector A points this way, and my vector B points like this. Okay. Now, so what is HA? Okay, if H is a scalar and we are not told whether H is positive or negative, then HA can possibly look like this. HA can possibly look like this, a lengthened version of A. It can also be a shortened version of it, depending on what the number H is. It is also possible to have opposite direction. Let's say HA looks like this. Right, so yeah, there are many possibilities on how my HA will look like, but one thing for sure is that my HA will be parallel to A for sure. Right? Then what about KB? There are also a few possibilities on how my KB will look like. So it could be a shortened version of B. It could be a lengthened version of B. I can also have opposite direction, or even like opposite but a shorter version. It all depends on what the number K takes. But one thing for sure, regardless of what number my K takes, it will be parallel to the original B. Okay. Then now, if I say, okay, for HA to be equal to KB, okay, we need HA and KB to have same direction and same length. Okay, same direction and same length. Okay. While it is not so hard to make them have the same length, just by modifying your values of H and K, well, it's not so hard to make them have the same length, but to make them have the same direction is almost impossible. Okay, so if you compare HA and KB, you compare the red color with the green color ones, okay, how to make them to have the same direction? Okay, as long as H is not 0, and K is not 0, it's impossible for your red and green vector to have the same length. And because one is slanted this way, the other is slanted that way. So it's impossible to make them have the same direction. Okay. The only way for the directions to be the same is that you set H to be 0. If you set H to be 0, then 0A will be just a dot. If you set K to be 0, then 0B will be just a dot. It is under this situation, this is the only situation where the two vectors can be equal. So the only way for HA to be equal to KB is when H and K are both 0. Okay. So that's why we have the first bullet point here. Okay. So if you have A and B being non-parallel and non-zero vectors, so this condition is important. A and B must be non-parallel and non-zero in the first place. Then if HA equals to KB, then both the coefficients must be equal to 0 for equality to hold. Okay. And the second bullet point is just an extension of the result that we have in the first bullet point. So here they are saying if you are given an equation, HA plus KB equals MA plus NB, you can always move the terms around such that A goes to one side and B goes to the other side. And then H minus M is just a number, N minus K is another number. Since A and B are non-parallel and non-zero vectors, the only way for the two sides to be equal is when both the coefficients on each side are both equal to 0. Or else this equality can never hold. So if H minus M is equal to 0 and N equals K equals 0, what it means is H is equal to M and N is equal to K. So if you look at this final result that we got here, it actually allows you to compare coefficients. Okay, so what is H and M? It's the original coefficients of A on both sides. And then what about K and N? K and N, they are also the coefficients of B on both sides. So this result actually allows us to compare coefficients. For the case when two non-parallel and non-zero vectors are involved in the same equation. I'll give you one numerical example. Let's say, given that AB are non-parallel and non-zero. Non-parallel and non-zero vectors. Okay, and you are also given that, let's say, k minus 2 a plus 3b is equal to let's say 4a plus m minus 6 b. Okay, so since a and b are non-parallel and non-zero vectors, from the earlier bullet points, we understand that it's actually okay for us to just compare coefficients. And so that allows us to form two equations. K minus 2 equals 4 and 3 is equal to m minus 6. So you can easily solve for k and m. And so k will be 6 and m will be 9. Yeah. So it allows us to compare coefficients. Okay. However, one thing to take note is if you have 3 or more vectors involved, if you have 3 or more vectors involved in the same equation, then things are not as straightforward. When you have 3 or more vectors involved in the same equation, then it is not always correct to compare coefficients. It's not always correct to compare coefficients. However, there is one special case. If you are given ijk, okay. Right, so for ijk, if the three vectors involved are ijk, then it's actually okay. It's actually okay to compare coefficients. But for if there are other three vectors, if you have, let's say, combination of vector A, B, and C, it's actually not always okay to compare coefficients. It's not always okay to compare coefficients because there are some other conditions to check. You have to make sure that it is impossible to get one vector by taking a linear combination of the other two, which I would not want to delve too much into it because that's not a focus on our syllabus. Okay, so in our syllabus, you just need to be aware that if the three vectors involved in the same equation are ijk, it's actually okay to compare coefficients. So if you are given, let's say, vertical bracket form, 3, 2, 4, is equal to, let's say, k minus 1, m minus 2, n minus 3. Okay. Then it's actually okay to compare coefficients because what we effectively have here is 3i plus 2j plus 4k is equals to k minus 1i plus m minus 2j plus n minus 3k. And so if the three vectors involved in the same equation are ijk, you can safely compare coefficient. If the three vectors involved are not ijk but just some random three vectors, then it's not always okay to compare coefficient. Just be aware of that. Okay. Okay. Now let's continue with example 2 here, just a very quick practice here to on how to prove that points are collinear. Okay. Given that mn is equal to this, u and v, they are just some random vectors. Okay, show that mn and p are collinear. Okay. So to show that, okay, so to show collinear, we need to show two things. Okay. The first thing is two vectors, each of them involving 2 out of the 3 points mn and p. So in this case, it's mn and np. Mn involve the points m and n. Np involve the points n and p. So these are two vectors that you can use to establish the first condition. So the first thing is to show that mn is parallel to np. The second thing to show is to note that there is a common point. In this case, the common point involved will be n. N is a common point. And then at the end only you conclude. Okay, now, how do we establish that two vectors are parallel? Recall the previous page. Page 1. Sorry, page 3. Okay, here. Okay, so notice that this statement here is if and only if and only if, which means that if you are able to establish that one vector is a number times the other, if you are able to establish that one vector is equal to a number times the other vector, then you can happily conclude that the two vectors involved are parallel. Okay, so let's start with Mn, and we try to write it. The aim is to get a number times with np. The aim is to get a number times np at the end. Now, so let's copy Mn first. So it is 4u plus 12v. 4u plus 12v. Okay. So one easy way to write this as a scalar multiple of np is, first we notice that of course np also involves u and v. And so in order to make this number become 7, you can do it in 2 steps. If you find it hard to do it in one go, you can do it in 2 steps. First thing is to factor out the 4 first. And so you have u plus 3v. Then what we'll do next is you want to make the coefficient of u become 7. You want to make the coefficient of u become 7. And so one very easy way to do it is you would introduce 1 over 7 and 7 u plus 3v. Okay, so I'm basically introducing a 1 there. I'm multiplying by 1 because 1 over 7 times 7 is just 1. So the equality is maintained and nothing changes here. Okay. Then next is that I'm going to combine the last 2 brackets together, and this number I will combine that. 4 times 1 over 7, I get 4 over 7, while the bracket at the back, it becomes 7u plus 21v. And what is 7u plus 21v? It is np. So I have 4 over 7 times np. Okay. So now what have we shown? We have shown that mn can be written as a number times np. Okay. The earlier page says if you can write a equals to kb, you can deduce that a is parallel to b. And so here mn is equal to a number times np, therefore mn is parallel to np. And so that is just the first thing to establish. And the second thing is to note that there is a common point. So we can write also note that there is a common point, or note that n is a common point. And therefore, points MNP are collinear and shown. And so there are 2 things to establish. First is to establish that the 2 vectors are parallel. So we have to show that one vector is a scalar multiple of the other. And then note that we have a common point n, then only the final conclusion. So make sure that you know how to manipulate the numbers in the process of showing that mn is equal to a number times np. And make sure that you know how to manipulate the numbers. Wei Feng say, can I state if mn is parallel to np, then mn equals to knb, then I compare coefficient. Uh, well, that is not encouraged. That's not encouraged because you need to establish that mn and np are parallel. I mean, parallel is not an information that you can use yourself. Well, if you use that method, right, I won't say it's wrong, but make sure you do it correctly. Yeah? Okay, so you can say, okay, consider the equation mn equals to k and p, where k is a scalar. Okay. Then you have mn. Okay, then you have what is it? 4u plus 12v is equals to k times 7u plus 21v. Okay. Uh, then I think you are stuck because they didn't say that u and v. They didn't say that u and v are non-parallel vectors. They didn't say that u and v are non-parallel vectors. So you actually can't compare coefficients. You are stuck here. You can't proceed to compare coefficients. And even if they do say, u and v are non-parallel and non-zero vectors, you will need to solve for k twice, Solving it once is not good enough. You have to solve for k twice and show that you get the same k. Yeah. So if for this question, you actually get stuck here. You actually get stuck here because you can't compare coefficients. They didn't say u and v are non-parallel and non-zero. Yeah. So in this question, this method doesn't work. Right, so I would encourage everyone to learn the more standard way of showing that two vectors are parallel. By doing some manipulation to the numbers. That is a more standard way. Okay. Before I start part B, let me just show you one example first. Okay. Okay. So let's say you are given A is equals to I plus J. Okay. B is equals to, let's say, 2I plus J. But obviously A and B are not parallel. So, okay, so let's say the question asks you, determine whether A and B are parallel. Yeah, of course, an exam question will not ask you a question as silly as this. This one is very obvious that A and B are not parallel, but I'm just trying to illustrate to you one fact. Okay. Determine whether A and B are parallel. Okay. So if you start off by saying, okay, if you let A is equal to KB for some scalar K, okay, then if you try to write I plus J is equal to K times 2I plus J, yeah, then of course I plus J is equals to KI plus KJ. Okay, then if you compare coefficients, here it's okay to compare because I and J are known to be non-parallel and non-zero. And so you will have 1 equals to 2K, and that gives you to K equals to half. Okay, so if you just stop here and you happily conclude, and you happily conclude A equals to half KB, sorry, A equals to half B, and then you say A and B are parallel, this will be a wrong conclusion. This will be a wrong conclusion. Right, so um, what you can do instead, what you should do instead is to solve for k twice, and then notice that k is inconsistent. Okay, so what you can do instead is you say 1 is equal to 2k and 1 is equal to k. So you get k equal to 1 half and k is equal to 1. And then you say the value of k is inconsistent. And therefore, A, B are not parallel. And then this is the correct way. Alright, so yeah, it's because when you first form this equation, you are actually not sure. You're actually not sure whether this equality holds or not. Alright, so you're actually trying to figure out that is there a value k? Is there a value k that will make the equality hold? So the proper procedure to check is you solve for k twice. You solve for k twice. And then check whether value of k is consistent or not. Later in this chapter, we will use a similar technique to do some different things. Yeah, I think Wei Feng has already answered Kushagra's question in chat. We cannot compare coefficients. Under the method that I show here, where I say stuck, the reason why I say we are stuck here is because we cannot proceed to compare coefficients. We cannot proceed to compare coefficients. You can only compare coefficients if you are told that U and V are non-zero and non-parallel. Yeah, that is the condition before you compare coefficients. Non-parallel and non-zero. Yeah. Okay. Yeah. So going back to part A just now, I encourage everyone to learn the more standard way. Learn this method here. This is a more standard way to establish that two vectors are parallel. Okay. Now, coming to part B. Okay, so coming to part B, you are given vectors A and B. In terms of ij are guaranteed to be non-parallel and non-zero. Because I is in the x direction, j is in the y direction, and these two, each of them has a length of 1. So they are guaranteed to be non-zero and non-parallel. Okay. So find the value of n if vectors A and B are parallel. Okay, so now they give you this information. A and B are parallel. A is parallel to B. This means A is equal to lambda B uh, for some scalar lambda. Yeah, I would encourage you to write the word for some scalar lambda, or alternatively, you can say where lambda is a scalar. Yeah, I would encourage you to mention the word scalar here. Yeah, if you forget to mention is actually not too bad lah. But it will be better lah. Because you're actually introducing a new symbol there. So it would be good to specify that that new symbol is a scalar and not a vector. Okay. Then next will be sub in your A and B. It will be lambda times with minus 4i minus 10j. N minus 2i plus n minus 1j is equals to minus 4 lambda minus 10 lambda j. Okay, then we say since I and j they are non-parallel and non-zero vectors, we have n minus 2 equals minus 4 lambda. Call this equation 1. And n minus 1 is equals to minus 10 lambda. Call this equation 2. Okay, the aim is to solve for n. And so you have a pair of simultaneous equations, two equations and two unknowns, it will be possible to solve. Okay, so the simple way here is take 1 minus 2, so you can eliminate n. You'll get minus 2 plus 1 is equals to minus 4 lambda plus 10 lambda. And that gives minus 1 equals to 6 lambda. Lambda equals to minus 1/6. And then you can just sub lambda equals to minus 1/6 into either equation 1 or 2. N will be 8/3. And that. And so when you have non-parallel and non-zero vectors and there are only two vectors involved, then you can safely compare coefficients. Okay, now we'll move to the next page. Okay, so hopefully up until this page, you still find this chapter easier. Right, so these are basically just a refresher of what you have learned before last time, right? Okay. Next is algebraic properties of vectors. So what are the operations that are allowed when you compute vectors in the algebraic form? Okay. So these are properties that you have been using all the while in your secondary school. And whether or not you are aware about all these properties, you have been using all those. So this is just to let you aware what are the properties that you have been applying all this while. Okay. So first of all, vector addition is commutative. Commutative means you can interchange the order. And so if you add, commutative means order can interchange. Order can be interchanged. So I'm talking about addition. Commutative is not true for subtraction. It's only true for addition. So a plus b equals b plus a. If a and b are vectors. Okay. Where you can interchange the order of a and b. Okay. Vector addition is associative. Associative means when you have three terms added together. So this is still talking about addition. When you have three vectors added together, whether you want to work on the first two first or the last two first, it doesn't affect the final result. It's just that when you have usual numbers, right? If you have 1 plus 2 plus 3, whether you want to do 1 plus 2 first or do 2 plus 3 first, it's the same. And so this will give you 3 plus 3 is 6. Then 1 plus 2 plus 3, if I do 2 plus 3 first, it's 1 plus 5, which is 6. So it's the same. But that's for usual numbers. So here, it's trying to tell you that this associative property is also true for vector addition. And whether you work on the first two or the last two first, it doesn't matter. Then next is when you have distributive property of scalar over vector sum. And so it will be easy to understand when you look at this equation here. Here lambda is a scalar. A and B are vectors. So you can distribute your lambda over addition of two vectors, just like how you would distribute like the usual what you do in the usual algebra. And so yeah, it's very similar to the usual algebra where you can just distribute the coefficient. Okay, so point number 4 is distributive property of vector over scalar sum. Okay, so you have two numbers added up, for example 2 plus 3, and you multiply by vector A, it's 2A plus 3A. And of course it becomes 5A eventually. And so this is trying to tell you that you can also distribute vector over addition of two numbers. Okay. Right. So there's nothing special to take note of about algebraic properties of vectors because it's consistent with usual algebra. Okay. Then next is resultant. Hi guys, can you hear me now? Hi guys. Okay. Yeah, and I've also started sharing my screen. Okay. Uh, wait, wait. Okay. Yeah. Now my screen should be back on. Okay. Yeah. Yeah. Sorry for the accident just now. I pressed the sleep button accidentally. Okay. Let's carry on with the next part. Okay. The next part is on resultant vector. Okay. So in this empty box here, I intended for you guys to draw a diagram. So the diagram that I want you guys to draw is this. So the description says AC is a resultant of AB and BC. So if you have A, B this way, A to B this way, and B to C this way, then A to C will be known as a resultant. A to C will be known as a resultant of A, B, and BC. We can also rephrase it and say A, B, and BC are the components of AC. And the triangle ABC is called a vector triangle. Since most of you guys are doing physics, you should be very familiar with all this. Right? So if you have one vector where the end of the first vector is the starting point of the second vector, which means the two vectors are connected end to end like this. Then starting from the very beginning to the very end, the single vector connecting the very beginning to the very end will be known as a resultant vector. Okay. Yeah, I think you're all familiar with this. Okay. Then next is addition of vectors. How do we visualize it? The so-called triangle law will be similar to the diagram that we draw above. Right, so if you have the vector AB followed by BC, where the end of the vector A is the beginning of the vector B, which means vectors small a and small b, they are connected end to end, then the single vector that connects the very starting point to the very ending point, this single vector will be known as a resultant, and you can write C is the result of A plus B. Okay, so addition of vector, when we visualize it, it means the vectors are connected end to end. Addition means the vectors are connected end to end. So A plus B means after A ends here, at the end point of vector A, we start the new vector B. Addition means the vectors are connected end to end. Okay, next. Parallelogram law. Okay, parallelogram law is not so frequently used in the exam question. Just sometimes in some special questions, like especially when questions where the diagram is given, if you're aware of this parallelogram law, sometimes it can help you to do things a bit faster. And so parallelogram law is only applicable for addition of two vectors. And this one is only applicable for addition of two vectors. If you have three or more vectors, then parallelogram law is no longer useful. Okay, so the idea is this: if you want to add up vector A and B, in this diagram, A and B are the components, to add up. And so you want to add up A and B. Okay, so the resultant, we all know that the resultant, you can do it using triangle law, right? So you can have your vector A maintained like that, but your vector B, remember the vectors are free, so you can always move your vector B to this side, maintaining the length and direction. And then you would get the resultant as this slanted red color one. This will be the vector C, the resultant. But then if you compare the triangle that I draw with the parallelogram printed here, the vector C is the same. Right? So this allows us to have another interpretation of addition of two vectors. Okay, so if you have diverging vectors, if you place your A and B diverging, this diagram will say A and B are diverging. This diagram will say A and B are diverging. Right, the word diverging means they have a common starting point. They have a common starting point and they point outwards. So for the case when A and B are diverging, you can actually try to complete the parallelogram. Using A and B as the two sides, you complete the other two sides, you complete the parallelogram. And then from the common starting point of A and B, if you connect a diagonal to the vertex at the other side, then this will give you the resultant. Yeah. And so it's just another mindset on how to get the resultant. So rather than using the triangle law, you have the option to use parallelogram law, which will give you the same resultant nonetheless. So this is just a different way of thinking to get the same result. Okay. Okay. Then next is polygon law. Polygon law is just an extension. This is just an extension of triangle law. So the triangle law in point number 1 is when we add up two vectors. So if you add up 3 or more vectors, of course you won't get a triangle, it will be a more complicated polygon. So it's just an extension. So it means that if we have vectors connected end to end, we want to add up A, B, C, and D. So we draw A. At the end point of A, we start the vector B. At the end point of B, we start the vector C. End point of C, we start the vector D. So the very beginning to the very end. So this will be the start, this will be the end. So this vector E here will be known as a resultant. And we can write A plus B plus C plus D equals E. So yeah, it's just an extension of triangle law. Okay, so to give you one more diagram, if I have like A pointed, okay, wait. If I have this is my vector A, this is my vector B, and maybe this is my vector C, and this is my vector D. Okay. So where is my starting and the ending? Here's the very start. Okay. So what's important is that you have a continuous flow. You have a continuous flow of the arrows. The vectors are connected end to end. So we have A followed by B followed by C followed by D in a continuous flow. And then this single vector that connects the very start to the very end, this single vector will be known as a resultant. Yeah. And so you have A plus B plus C plus D, it will be equals to the resultant, let's call it R. So it will be equals to R. Okay. Yeah. As simple as that. Okay, next. Subtraction of vector. Okay, subtraction is a very important thing that we will use again and again in our syllabus here. Especially properties 2 and 3. Okay, property number 1 is telling us that if you have a vector directed from A to B, okay, so we all know what negative of AB is. Okay, we all know what negative of AB is. So if this vector is a vector from A to B, then the negative of A to B will point the other way, and negative of AB will point the other way. And negative of AB is also the same as the vector directed from B to A. Right? Okay, so this means yeah, and of course you can move the negative to the other side, and you write AB equals to minus BA. So this property number 1 here, it allows you to interchange the order. So when you have a vector presented in the form of 2 capital letters denoting the starting and the ending point, it allows you to interchange the order of A and B by putting a negative in front. So for any random points, let's say I have Mn, Mn will be equals to negative of Nn for sure. And for any random points M and N. Another example, PQ will be always equal to minus QP for any 2 random points P and Q. Okay. Then second and third, these are very important. Okay. Now, if you visualize the diagram A to B, okay, the origin O, it can be somewhere very far away. In fact, we don't care where O is. And so let's just depict O as a very far away point. Now, to get from A to B, I can break it down. I can break it down into a longer path. I can travel from A to O first, then only from O to B. So which means that I can write AB as the sum of AO plus OB. Because my 2 green colored vectors are connected end to end. So AO plus OB, the resultant will be AB. But then according to property number 1, if I don't like to see AO, I like O to be in front, then I can write OA with a negative in front. Property number 1 allows us to interchange the order. Now I can rearrange these two terms. I can write as OB minus OA. So this is a result that you need to understand and apply very frequently. This means what is OB? This is position vector of B. OA is what? It's a position vector of A, which means for any vector AB, for any vector, it can always be broken down into position vector of the ending point minus position vector of the starting point. Okay, give you another example. PQ can be always written as OQ minus OP. It is always O to the end point minus O to the start point. Yeah, Q is the end, P is the start. Right, so for any vector, whether it's A, B, P, Q, or whatever, for any vector, it's always possible to write it in terms of the position vectors, and it's always O to the n minus O to the start. It's always O to the n minus O to the start. Right, so the third property there is just application of the same technique. Right, so in this case, because A is the ending point, A is the ending point. Right, so you have O to the n minus O to the start. And that's it. Right, so this is a very useful property that we'll use very frequently in our syllabus. And so be familiar with this. Okay, next is midpoint. In coordinate geometry, we have learned before midpoint. When it comes to vectors, it also have a formula that looks very similar. The only difference is that now, instead of using coordinates in our computation, we'll use position vector instead. Okay, so let's first consider let's just consider a 2D diagram first. A 2D diagram. Let's say my point A is having coordinate x1, y1. Point B is having coordinate x2, y2. Okay, we all know that the midpoint formula is x1 plus x2 over 2, y1 plus y2 over 2. And now I will just give you the result first, and you will see that the result for vectors, the form of it is very similar to the coordinate formula. Okay, so the formula is this: OM will be equals to OA plus OB divided by 2. So if you look at the form of it, it is something divided by 2. It is okay. So in the coordinate form, you have x1 plus x2 over 2. X1 comes from the point A. X1 comes from the point A, while your x2 comes from the point B. So here is a similar thing. You have the position vector of A, position vector of B, and divided by 2. So if you compare the form, it's of a similar form. So it should be very easy to memorize, where you take an information from A plus with another information from B, then divide by 2. That is the same formula. Okay, vector formula is more convenient and compact because you don't have to deal with x, y, z coordinates separately. Because the position vector itself already brings the information of the x, y, z coordinates in one go. Right, so yeah, so basically the midpoint formula for vectors, it is the same idea and concept as the midpoint formula using coordinates. It's just in a more compact form. And because position vector itself already carries the x, y, z coordinates. Okay. Right, so yeah, the same will be applicable for 3D as well. Okay. So another way to understand it is that if you have, okay, so in this box, you can draw this diagram here. The statement says let M be the midpoint of AB. Okay. Let M be the midpoint of AB. So let's suppose that O is a very far away point. It can be anywhere, it doesn't matter. Okay. So now the midpoint formula printed for you in the purple box here, it will give you the position vector of m. Position vector of m. It will not give you coordinate, but it will give you position vector. But then we all know position vector can be easily converted to coordinate format, right? Then now if you look at this diagram, okay, my intention is to get a formula for OM. Okay, now I'm trying to show you how this formula can be obtained by using algebraic manipulation. Okay, now the intention is to get from O to M. Okay, of course, I can take a longer path, right? I can take OA, then followed by AM. So the first thing I can write is this. I can write OM is equal to OA plus AM. Okay, now I would want a formula in terms of OA and OB. Okay, I want a formula in terms of OA and OB. So first of all, we notice that AM is half of AB. According to our diagram, AM has half the length of AB. AM has half the length of AB and they're in the same direction. So it's obvious that AM can be written as half AB. Okay. So you have OA plus half AB. Okay, I'm replacing AM by half AB. Okay, then using the subtraction formula that we have in the previous section, AB can be written as O to the end point minus O to the starting point. Okay, O to B minus O to A. Then distribute your half, distribute your coefficient of half. Minus half OA. Simplifying the coefficients, you have now half OA plus half OB. Factoring out the half, you have half times OA plus OB. Yeah, so this is how the formula is obtained. OA plus OB over 2 is the same thing. Yeah. Okay, in the exam, you won't be asked to derive this formula. What's important is you know how to apply it. Right? Okay, then we have 5 minutes left. Let's do one more example and then we'll end the lesson today. Okay. Right, referred to the origin O position vectors of A, B, and C are given as this. Okay. Usually when we are given information in terms of IJK, it's not very computation friendly. I usually don't like things written in terms of IJK when I do computation because I find it quite messy. So I believe most of you will feel the same also. And so if you have a choice, you would prefer to do your computation in terms of vertical bracket form, so that you don't have to keep writing the IJK. So yeah, we are always allowed to convert the IJK format into the bracket format. You are always allowed to do that conversion to ease your computation. Okay. So usually what I will do is to list down the information first in bracket form. And so I am given OA equals to A, which is 223. OB is given as B, which is 145. OC is given as C, which is minus 18P. Here's the unknown P. Okay. Right, now they say find the value of P if A, B, and C are collinear. Okay. A, B, C are collinear. Okay. A, B, C are collinear. This means if we form any two vectors using the points A, B, and C, they are guaranteed to be parallel, right? So we just simply form two vectors. So we can say AB is parallel to BC. That means AB is equal to lambda BC for some scalar lambda. If you want to use K also can. If you want to use k rather than lambda, also can. It doesn't matter what the symbol you use there. As long as you don't use p, because p is an unknown that is already there in the question. Okay. Then AB can be written as OB minus OA. BC can be written as OC minus OB. Okay, now it's time to sub in the values. Okay. OB is 145, OA is 223, OC is minus 18p, then just sub in the values. This is 145. And so when things are written in bracket form, it's very easy to do computation. Whether you need to do addition or subtraction, you just add or subtract component by component. So 1 minus 2, it will give you minus 1. Minus 3 is 2. This is lambda times negative 2, 4, and p minus 5. Minus 1, 2, 2 is minus 2 lambda, 4 lambda, and p minus 5 times lambda. Right. So okay, when things are written in vertical bracket form, you can safely equate component by component. You can safely equate. It's because this is effectively equation in terms of ijk on each side. And earlier I said when you have equations in terms of ijk, we can safely compare coefficients. You can safely compare coefficients. Okay. So just compare component by component. And the aim of this question is to solve for p, but then the equation involving p also involve lambda. So it won't be helpful if you start by comparing the z component. And because it will involve two unknowns, you won't be able to solve for p yet. So you want to solve for lambda first. And so you either take the x component or y component to use first to get lambda. Okay. So minus 1 equals minus 2 lambda, which means lambda equals 1/2. Then you have 2 equals to p minus 5 lambda. 2 is equal to p minus 5 times half. You have now 4 equals to p minus 5 and p equals 9. Done. Okay, that's the final answer. They ask for p. Okay, done. Okay, Rania asked in chat, can I skip the step of multiplying lambda in the brackets? You mean you stop here and then you jump to here lah? Okay, I would say okay lah. Can. Yeah, although I don't really encourage you to jump that way. But if you insist on jumping, I'm fine with it. Okay. So that's it for example 3. The time is now 11:02, so it's time to stop. Okay, so we have covered quite a lot of chapter 9A today. I hope you still find it simple. Whatever that we have covered today, I hope you still find it simple because the difficult part, there are much more difficult part that will come later in the chapter, especially in chapter 9B and also FP1 chapter 1. The difficult things are all there. And so okay, we'll continue with example 4 on Tuesday. Okay, so I'll see you again on Tuesday then. That's all for today. Thank you, everyone. You may leave the video meeting.
Thank you, sir.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.